So we've got two projects very closely related underway in the centre. And they both concern islands, and they both concern how we set priorities for management spending and management action within and between islands. We've got the first one to get up was the Southern Great Barrier Reef, funded by the National Environmental Research Program, Tropical Ecosystems Hub. And then a little after that, we had some funding from Western Australia as part of the Gorgon-Barrow offset scheme for the Pilbara Islands. The problem statements are fairly straightforward. The solution's not necessarily, but the rationale, I think, for the projects is fairly straightforward. There are lots of islands to be managed. John mentioned a number of about 1,000, depending on how you draw the lines in the Great Barrier Reef World Heritage Region. Just in that southern area that we've defined in the GBR, there's 300 to 400. We're tackling, in the short term, 300 or so off the Pilbara coast, but there are hundreds more, depending on how that project pans out. There are lots of features. I'm calling them features. Other people call them values or assets of local, regional, national and international significance on these islands. Some endemic species, some species that simply don't occur anywhere else except one island. And then you've got nationally, internationally significant breeding colonies for seabirds, turtles. You've got vegetation types that have been reduced on the mainland. There's a long list of natural values that managers have to care about. And there are dozens of threats to those values arising from introduced species, visitation, fire regimes, lots of arguments about what makes up an appropriate fire regime, depending on what you think the natural state should be that you're aiming for. And those threatening processes combine with a lot of islands, a lot of features to make this a very complex problem to deal with. There's not enough people, there's not enough money, there never is really for conservation. And so someone has to set priorities, and the managers both in WA and in Queensland have been fairly clear that they would like a more explicit way of doing that, so that when they do set priorities, they know that they're getting the best outcome, once that outcome's been fairly carefully defined, for the money they have, and that they can be accountable. They can say to someone, this is the way we've decided to spend our money because we can demonstrate it's actually the best way to spend what we've got. So we've come up with a preliminary, I've called it an operational model. It's just basically a diagram of what a decision support system would look like. There are lots of these in the literature. This one's a bit different, but there are lots of ways of cutting the cake. And I don't want to step through this bit by bit. It's just to say that it's possible to say this is a way of gathering information, organising it, combining it and analysing it to get what managers want. So importantly, some of the main features of this diagram are some guiding principles or some goals, data on features leading to objectives, identifying the areas that we're managing, which are mostly going to be small islands in their entirety, but some of the big islands will need to be subdivided, thinking about the actions that are needed, what sort of contributions they can make to averting threats, how much they're going to cost. The whole thing is formulated mathematically, but then linked to some software with a GIS interface with which managers can interact. So they can ask questions, see the answers. If they don't make sense, go back and find out why. Sometimes it will be because there's been a mistake in the parameters. Sometimes it will be because the best solutions are not always intuitive to start with. So that's the overall picture. Maybe the most distinctive things about this are, first of all, the fact that we're focusing on explicit actions for explicit places, There is a literature on that, but it's a small one. And the other thing is we've got, some of these models end up being fairly complex. These little arrows here with the shaded boxes. Modelling threats is in fact a modelling job on its own. It has to be dynamic because your actions will alter the threats. The threats might interact. I'll talk a bit more about this later. One of the messages to take from this is that what systematic conservation planning does and has tried to do for 30 years is to process information in this way with explicit objectives, and the priorities emerge from that process. And I think we get a better result. In fact, I'm sure we get a better result from this sort of process than one based on a simpler scoring approach or ranking approach. There are 4 things that I want to talk about as, for me, being quite exciting about this process and pretty distinctive. One of them is the active involvement of managers. In a way, for me, this is a dream project because it's challenging science. We've got the funding to do it well, and we have managers involved from day one. So at the bottom, those photos there are a reconnaissance trip we did with some Queensland Parks people late last year. These folks have been talking to me since well before we had the funding, saying we need to somehow link what you guys do with spatial prioritisation of what we're doing. Now we have the funding. And and that's the point I was just making. There's a lot of support for this project from managers at a range of levels because they can see that there's a benefit. And the fact that they're involved in actually shaping, giving us the data, in many cases, shaping the software, discussing the approach, means that when it's finished they will understand it and they'll be interested in using it. A second thing is, for me this is exciting, the complexity of some of these submodels, and I'll just give you an example in the case of cost. So normally what we've done in conservation planning, if we've used actions, specific actions at all, is to say what do these things cost per unit area, what are their contributions to averting threats or contributions to objectives, and those stay constant. But in reality, there's nothing like that. There are dynamics in space and time. And those circles are just to highlight the dynamic parts of this overall operational model. 3 examples of complexity of costs. One is that the cost of going to an island and doing an action actually depends on what other islands you're going to on that trip and what route you're taking. If you go out specifically for one island, clearly it's going to be a lot more expensive than if you go out and that one island is part of an itinerary of 12 or 13 others. So that has to be factored in, and that cannot be factored in as a fixed value. That's got to happen each time the logistics of a trip are planned. There are some temporal dynamics as well, because we know there are lower costs of controlling outbreaks, say, of weeds, if you get in early than if you let them get away. But you can't always get in early. For every outbreak, there are too many outbreaks, so you've got to choose which ones. And you'll notice I'm focusing almost entirely on terrestrial threats, and that's the focus of both of these projects, but this whole approach hopefully will broaden later to intertidal and marine areas around islands. A third example is that what we often find with government funding, so controlling goats off Mackay, on islands in Mackay, is there'll be a pulse of funding. People will shoot goats, they won't get them all, the money will run out, the goats will build up again, somebody eventually will say there's too many goats, there'll be some more funding for goats, and we'll go through this cycle, and we don't really know, what the benefit of that is, but it's safe to say it's a pretty costly way of doing it. So the lack of follow-up can be costed into these dynamics as well. And again, we won't always be able to follow up. Data requirements are enormous, and I'll illustrate this in the next slide, but we're trying to get a lot of information together, and we're trying to do it in a way where we have explicit uncertainty around our variables. The basic data table for conservation planning is a matrix of I just realised I didn't set my watch. So I've been going for, 2 minutes? I'll try and be quick. Where was I? The basic table for conservation planning is features, species, ecosystems times, let's say in this case, islands. And any data table for conservation planning has got lots of false negatives in it. We never have all the information that's out there. So what we try to do is fill as many of the false negatives up as possible without putting in false positives. And we're doing that fairly exhaustively for a subset of islands in the GBR right now, and we're beginning the work in WA as well. We're relying on all sorts of published sources, museum records and so on, all the usual records, reports, scouring them, but also sitting down with managers to pick their brains, because there's a lot of information in their heads that is not written down or available in databases. As we go into the other kinds of data, so that's just one data matrix, for each threat we need a modified features times island table to indicate how those features are going to fare over some time frame in the absence of intervention. For each of our actions that we decide to apply, we will need a modified version of the threats applying to the features times islands table. So you're starting to get the idea that we cannot deal with a lot of threats and a lot of actions, or this thing will just explode out of control. It's already very ambitious. And then we need to know the costs of particular actions per unit area per island, and they will vary as well for a whole range of reasons. And as we go from the basic data table into costs and actions, we're relying more and more on the expert judgment of managers. And we've spent a fair bit of time talking to folks, Mark Bergman's group in Melbourne and others, about expert elicitation techniques, not only to get the most reliable data, but also to have explicit uncertainty bounds around our data, the best guess, what the upper bound might be, what the lower bound might be for each of these values, so we can use that uncertainty explicitly in this work. A diagram that I struggled to put together earlier today, there's been a fair bit of work, as I said. Well, there's been maybe 20, 30 publications on multiple action explicit systematic conservation planning. A lot of it's been at a remarkably broad level globally for ecoregions. But, and this graph is saying something about the size of management units on the horizontal in kilometres squared and the number of management units we're trying to deal with. I don't think there's a lot of point in being over on the right-hand side. You can get a paper in PNAS for that, but nobody manages an entire ecoregion with one action. The algorithms might be good and they might be adaptable to the kind of problem we're dealing with, but as you move to the left of that horizontal axis, you're much more relevant in terms of being down at the scale at which people actually do things on the ground. We've done some work. Mariana Fuentes, who couldn't be here, has done a very nice piece of work on multiple actions for managing flatback turtles in the Gulf of Carpentaria, using fairly fine scale, fine resolution analysis for a small number of sites. And that was difficult, direct elicitation of all that information. When we move up into larger numbers of sites, which we're trying to do with these projects, the approach typically has been spatial modelling, which comes with a lot of error, which means you get down on the ground and you find out mostly you've got it wrong, more or less. And you've got a lot to get wrong. The more parameters you put into these things, the more mistakes you make. What we're trying to do is spend a lot of time on direct elicitation and use spatial modelling only when we have to. The final thing is that new software will be necessary, and thanks to the funding from WA, we have the resources to develop that. None of the available software systems will do the job that we're trying to do. The new software also will be developed, is being developed with managers from the ground up, so that they can inject their thoughts and their requirements into it. It'll be linked interactively to a GIS interface. And one of the exciting parts of getting the data together for me will be the sensitivity analysis. So we can ask a question like, how much does it matter to our priorities if we have pretty crappy data versus really exhaustively collected data? There's no way of answering that unless you've got really exhaustively collected data and you lose data from that data set selectively. You degrade that data set and then you find out what happens to your priorities. And that's why it's worth the investment in doing this. And we can also do some sensitivity analysis in terms of exploring the uncertainty bounds. What if we're risk averse, risk seeking? What's the worst case? What's the best case? How much difference does it make? And finally, the software will allow us to ask questions in two ways. One will be to say, what's the best we can do with a given budget? If this is our annual budget. Or we can say, what if we doubled the budget or halved it? But probably just as importantly, we could say, all right, if we take a policy statement that says what this government is going to do about GBR islands or something else in the next 5 years, we can actually cost it out. And when we've done that in the past, the numbers have been fairly scary, but sobering nonetheless in terms of validating policy statements. I mentioned our funding bodies for this, and I want to acknowledge 11 people in that list who are involved in the WA and GBR projects, both in the management authorities in WA and Queensland, but also at James Cook University. And we're working hard and we're hopefully breaking new ground. Thanks a lot.